All right, let's talk about thermochemical equations. The thermochemical equation is the chemical equation for a reaction, including the phase labels, that's important, in which the equations is given a molar interpretation and the enthalpy of reaction for these molar amounts is written directly after the equation. In other words, you write your normal balance equation, and after that you write your delta H with its numeric value of heat. Example, I got 1 mole of nitrogen gas. If I react that with 3 moles of hydrogen gas, I'm going to form 2 moles of ammonia. Okay, that's my stoichiometry recipe. In the process, though, 91.8 kilojoules of heat will be involved. Since there's a negative sign, okay, then we're talking about an exothermic reaction, which means I have 91.8 kilojoules of energy being released. Okay. Now remember that this is an extensive property. So it depends on the amount of substance to how much heat is going to be released or absorbed. In this case, released. So let's change this. Let's change my recipe. Let's say instead of having 1 mole of N2, I use 0.5 moles of N2. Well, that would mean stoichiometry that I would need 1.5 moles of H2, which would mean that I would form 2 moles, would mean that I would form 1 mole of NH3. So I've cut everything in half. The amount of nitrogen has been cut in half, the amount of hydrogen has been cut in half, and the amount of ammonia product is going to be cut in half. Since this is an extensive property, then how much heat is going to be generated? Half the amount, which means then I will be given an exothermic amount of 45.9 kilojoules of heat. Now what if I doubled the amount of nitrogen and doubled the amount of hydrogen, which made double the amount of ammonia? Then how much heat is going to be released? Double the amount, okay? Because of the fact that it's an extensive property. Now, if delta H has a superscript on it, like this, okay, where we have that superscript and that means that we're talking about thermal standard conditions. It means that we are at 25 degrees C or 298 Kelvin in 1 atmosphere. So anytime you see that little superscript, that tells us the temperature and pressure, your thermal standard conditions. The following are 2 important rules for manipulating thermochemical equations. Okay, you may recall we talked about this when we were dealing with K's. Okay, but we had different math involved there. Okay, when a thermochemical equation is multiplied by any factor, the value of delta H for the new equation is obtained by multiplying the delta H in the original equation by the same factor. Because of its extensive property, this is the case. Look at this. 2H2 plus O2 gives me 2 waters, which has a delta H of a negative 483.7 kilojoules. Now, if I'm going to take this and now multiply that by 2 factor, okay, then I'll get 4 H2s, 2 O2s, 4 waters. I've doubled the recipe, so I'm going to end up doubling the amount of heat generated with this equation. So then what happens is I double my delta H by multiplying that by 2 as well. Now remember, when we did this with the K expressions, since we're talking about mathematics and each one of those coefficients is to the order of that reactant, so it's going to that power, we had to do K to the n power. Okay, we didn't multiply by it, we went K to that factor of 2 to that power. Okay, got to make sure you know the difference, because on the final you have this stuff as well as the K. Second important rule is when a chemical equation is reversed, the value of delta H is reversed in sign. So if I take water here, my 2 H2s plus O2 give me 2 waters, which is a negative 483.7. Okay, that's an exothermic reaction. Okay, since it's a negative value. If I take the reaction now and flip it, now I got 2 waters, gives me 2 H2s plus O2. I have to change the sign of that delta H, which is now positive. Okay, so the first reaction is an exothermic reaction. When I flip the reaction, now the opposite process is happening. Now it's an endothermic reaction. Now when we deal with K's, when we flip the reaction, well, what we had before was products over reactants. If I flipped the reaction, then I had reactants over products, so the K was the reciprocal, 1 over K. So make sure you realize the difference of the rules and when we do one versus the other. Then we took the K's and we multiplied the K's. Once we added up the equations, we multiplied the K's. In this case, what we're going to do is we're going to add the delta H's. Okay, what we're doing basically is Hess's Law. Hess's Law of heat of summation states that for a chemical equation that can be written as the sum of two or more steps, the enthalpy change for the overall equation is the sum of the enthalpy changes of the individual steps. So basically, if I can take the reactions and products in different individual steps and I can add them like algebraic quantities and basically solve for the overall equation that I'm looking for, then I can add up the enthalpies and then give me the enthalpy of that reaction. When we did the K stuff, what we had to do is multiply the K's to get to that K of the overall reaction. So what we're doing is a simple example. Okay, what's going to happen when you use Hess's Law is you're going to be given some information, some equations. Could be 2, could be 3, 4 equations. Okay, and what you're going to do is take those equations and we're going to manipulate them and then see if we can add up those equations to give us to the equation in question. Here's an example. I want to find the delta H of 2D goes to B plus 2E. So I'm going to take those two equations given to me, manipulate them to solve for that equation. And if I get that, then add up the delta H's and it gives me the delta H of that equation. So what I tend to do is go one species at a time and try to see if I can find that species in one of the equations. Okay, I want it in one of the equations. If I find the species that's in both equations, then I'm going to skip that and move on to another one. What I'm looking for is to be able to manipulate one of those equations with that one species in it. That way I can say once I have that the correct number of moles and on the right side, I can say that equation's done and then move on. Okay, so I'm looking for that species in one of the equations. That way I can ask myself two questions. One, is it on the correct side? And secondly, is it the correct number of moles? If I can fix those two things, okay, with one particular equation, then I know that equation's done, okay, and I can move on to the next one. Let's look in this example. Looking for D. I want to find D in just one of my given equations. Can I find that? Yes, I can find it in the first one by itself. Okay, if it was in both of them, then I would skip it and move on to something else. Okay, I would only deal with it in both of them if I have to. Okay, I would move to the simple things first. Now I'll ask myself the first question. Is it on the correct side? I need it on the reactant side. Is it on the reactant side in my given? And the answer is yes. Okay, so I don't have to flip it. So I would use the equation just like it's written. Next equation. Is it the correct number of moles? Well, I need 2 moles of D. And in my problem, I have 1 mole of D. So no. So I'm going to have to multiply it by some factor to get it to be 2. Well, what would I multiply it by? Well, I'll multiply it by 2. Okay, then that way I get my 2D. So that means in the first equation will become 2A plus 2D gives me 2E plus 2C. And since I did multiplied everything by 2, then I have to multiply my delta H by 2 as well. Next, I'll go to the next species, which is B. Okay, and I'm going to see if I can find B in one of the equations by itself, hopefully in one of the equations that I haven't did anything to. And in this case, the answer is yes, there is. It's going to be in that second one. So then I ask myself the two questions. Is it on the correct side? And the answer is no. It's on the reactant side in the given, and it's in the product side in the question. So what I'm going to have to do is flip it. Okay, so when I flip it, I'm going to have to change the sign on Y. Okay, so we're going to end up flipping it. Okay, which means I'm going to change the sign on that Y. Next question is the correct number of moles. Well, I need 1 mole, and it is 1 mole, so I don't have to multiply by any factor. So I'll just take that equation and flip it. What now gives me 2C on the reactant side, 2A and B on the product side, and then I change the sign on Y and make it a negative. Now I'll add the two equations. Okay, I'll go ahead and add my two equations since I did something to every equation. Add them up and see what I get. I can see that my 2A's cancel. My 2C's cancel. I can see then I'm left with 2D goes to B plus 2E. The question is this the same reaction that I'm trying to look for? And the answer is yes. You should take the 10 seconds and write out all this information, okay? Write your equation, flip it, multiply by a factor, add them up, and see if it gives you the equation you're looking for. If it doesn't, that means you made a mistake. You need to go back. If you're given 3 or more equations, most likely you're going to have to use them all. Sometimes you have to use it to get rid of the intermediates, okay? So you have to make sure you check it. Take the 10 seconds, write it all out, see if it adds up to what we're looking for. Okay, don't just multiply numbers and add them. Make sure you're taking the time to write out everything. Well, since this does add up to the equation in question, then all I got to do now is add up my delta h's, which would then mean it's 2x minus y. Let's look at a real chemistry problem now. Here's my givens. I have sulfur plus oxygen gives me sulfur dioxide. It has a delta H of a negative 297 kilojoules. And I have 2 sulfur trioxides gives me 2 sulfur dioxides plus oxygen, which is a delta H of 198 kilojoules. The question is, okay, here's my question. Okay, I have 2 S's, 2 sulfurs plus 3 oxygens. I'm trying to make 2 sulfur trioxides. I want to know the delta H of this reaction. So for whatever reason, I can't do it in a laboratory, whatever, I'm going to go to tables, look up delta H of reactions I have. Take that, and I found out these 2 equations are there. So I'm going to manipulate these 2 equations to equal out to this equation in question. So I'm going to go through the species one at a time and see if it is in one of these reactions by itself, and then ask myself just 2 questions. So look at the first species, sulfur. Can I find that in one of the 2 equations by itself? The answer is yes in the first one. So then I'm going to ask myself those 2 questions. Number 1, is it on the correct side? The answer is yes. It has to be on the reactant side, and it is. Is it the correct number of moles? I need 2 moles of sulfur in my question. How many am I given? 1. So then I'm going to have to multiply everything by 2. So I'm going to have to multiply that whole equation by 2. Okay. Next in line is oxygen. I was going to try to find that in one equation by itself. But you're going to notice oxygen's in the first equation as well as the second one. So I don't want to have to deal with the math and combining the 2. So if I can get away without having to do that, I'll move on to another species and see if I can manipulate every equation with something by itself first. And if I can't do that, then go back and have to work out the multiple species in different equations as well. So let's look at SO3. Can I find that? Hopefully I'll find it in the equation by itself that's left. Okay, the answer is yes. I can find it as SO3 in that second equation. Ask myself the 2 questions. Is it on the correct side? The answer is no, which means I'm going to have to flip it. Is it the correct number of moles? Yes, I need 2 moles in my question, and I have 2 moles in my given. So all I have to do is just flip this reaction. Okay, I'm just going to have to flip it. And then add up the 2 equations and see if I solve for the equation in question. So the first equation, we said that we're going to multiply by 2, so let's do that. So I got 2 sulfur solids plus 2 oxygens gives me 2 sulfur dioxides. And since I multiply everything by 2, that means I'm going to have to multiply my delta H by 2 as well. Then we said that we're going to take the second equation and flip it. So I'll do that. So now I got 2 sulfur dioxides plus oxygen gives me 2 sulfur trioxides. And since I flipped it, I need to take the delta H now and change the sign. Okay, by multiplying by number -1. Next, what we're going to do is take the 2 equations and add them up. Okay, when I add them up, let's see what happens. Well, my sulfur dioxides will cancel. Okay, my sulfur comes down, my 2 sulfurs come down, my 2 oxygen and 1 oxygen add up to 3 oxygens, and my 2 sulfur trioxides come down, which gets me my equation. Is this the equation that I was looking for? And the answer is yes. Okay, I was looking for 2 sulfur solids plus 3 oxygen gases gives me 2 sulfur trioxides. So then I did everything correctly. So all I got to do now is add up my delta H's, which gets me a delta H of a negative 792 kilojoules. It's got a negative sign, so this is an exothermic reaction. Homework 45 deals with using Hess's Law. The biggest thing about this homework set is that you probably run into some fractions, so make sure you're up on how to add and subtract with fractions, common denominator type stuff. Other thing I like to caution you on is when you work problems like this, go ahead and write out the equations totally. Don't just take numbers and multiply them. Okay, what you want to do is write out the equation to make sure that your final answer is exactly what you're looking for. To make sure that you have intermediates cancel out. Sometimes you were given an equation and you need it to get the intermediates to cancel out. Okay, so make sure you're handling all the equations, add them up, and it gives you the equation that you're looking for. If it doesn't, that means something's wrong and you need to go back and see what's going on.